Uh, okay, yeah. So hello everyone and welcome to another session of the Bangalore Theory Seminar. Today's speaker is Manaaswi Parashar, who will give a talk on making quantum query algorithms robust to a faulty oracle. Manaaswi is currently a postdoc at the Center for Mathematics of Quantum Theory, University of Copenhagen, where he is hosted by Laura Manchinska. Prior to this, he did his PhD from the Indian Statistical Institute, Kolkata, under the supervision of Saurav Chakraborty, followed by a postdoc at the Department of CS, Aarhus University, and then a postdoc at the Department of CS, University of Copenhagen. His research interests lie broadly in quantum computing and computational complexity theory, and specifically in quantum communication complexity, quantum learning theory, and quantum query complexity. Over to you, Manaaswi. Manaaswi, you are currently muted.
Yeah, thanks. Thanks, Agrim, for the introduction. So let me get started by thanking Chandan for inviting me to give this talk. And thank you all for coming to the talk. So as Agrim mentioned, so I'm going to be presenting a joint work with David and Laura. And the title of the talk is Making Quantum Algorithms Robust to a Faulty Oracle. Right. So let's get started with a little bit of context. So we know that quantum computing is a very popular area these days, right? And sort of the reason for this is that there are certain problems that quantum computers can solve much faster than classical computers. Okay. And two famous examples of such problems I've mentioned here. So the first one is factoring. For this problem, there is a quantum algorithm known as Shor's algorithm, which gives a super polynomial advantage over the best known classical algorithm, right? And another problem is of unstructured search, where this algorithm known as Grover's algorithm gives a quadratic advantage over the best classical algorithm. So the problem of unstructured search is the problem of finding a specific marked element, an element which you want to find, given a list of elements. So we'll define this problem later on. Okay. And it turns out there are many problems which we get a quantum advantage. And these advantages are can be polynomial, super polynomial, and even exponential. And an excellent place to find problems which have quantum advantage is this website known as Quantum Algorithm Zoo, which is maintained by Stephen Jordan. Right. But although quantum algorithms can possibly solve certain problems much more efficiently, we do not have quantum computers with us today, right, to solve these problems. We have small quantum computers, but we do not have large scale quantum computers. And sort of the main reason for this is that noise. Okay, so quantum systems are highly susceptible to noise, and this noise usually comes when the system interacts with the environment. And as it turns out that it's very hard to deal with quantum noise. And also one of the reasons is that the quantum noise is fundamentally different from classical noise. So this is something we will see in this talk. Okay. So one of the most important questions today is to understand and mitigate noise in quantum computing. Right. And as it turns out, these algorithms that we talked about, factoring and search, both of them are quantum query algorithms. And in fact, almost all problems where quantum has a provable advantage over classicals is in this model, the model of query complexity. So we'll be defining this model later on. This is just like a high level overview. So given this fact, a natural question is to understand and mitigate noise in the quantum query model. Okay. And people have studied this question extensively over the past, but most of the work has been limited to the problem of unstructured search. And people have studied various noise models, right? And there has been little understanding for other problems. Along the way, there have been several open problems and conjectures. Okay, so I've written three such conjectures here. So the first conjecture asks that is there any fault model for which a quantum speedup is achievable? right? The third question is of a similar flavor. It asks that is quantum speedup possible with a faulty oracle, right? And the second conjecture says that such a speedup is not going to be possible in any noise model. Okay. Uh, and sort of the main takeaway of this talk is the following. So what we are later going to show is that a quantum advantage is retained for every quantum query algorithm that is sufficiently fast under a natural noise model. By sufficiently fast, I mean, let's say if a quantum algorithm has a supercubic advantage, a roughly supercubic advantage, then some quantum advantage is still going to be retained, even when we consider a natural noise model. And what is this natural noise model? So this natural noise model is the same model for which the conjecture 1 and 3 were made. Okay, and it is closely related to the noise model for which the second conjecture was made. So although I haven't said anything much till now, but still, are there any questions?
Yeah, I just want to take, is the quadratic speedup considered sufficiently fast in this definition?
Yeah, so right now any speedup that quantum can give you is interesting. Right. So yeah, it's great to have exponential or super polynomial speedup, but the quadratic speedup. Uh, so in particular, for this problem, unstructured search problem, it becomes very useful. So yeah, it's important.
Okay, thank you.
Good. All right. So with that being said, this is the plan of the talk. So we'll first look at the query model. So this is the model of computation that we are going to work with. Okay. So we'll first define the query model. Then we'll define the noise model. Okay. The kind of noise that we'll be dealing with. And we'll also look at the issue with quantum noise. Then I'll be stating our main result and we'll go to the proof ideas and we'll finish with a small list of open problems. Right. And this talk is planned to be around 40-45 minutes. So feel free to stop me at any time and ask questions. Okay. So let us start with the query model. So query model is a model of computation. And we are going to start with the classical query model. Then we'll go to the quantum query model, right? So in the classical query model, the goal is to design a randomized algorithm that computes a known function f on an unknown input x, right? So the function is known to us, but the input is unknown. And how does the algorithm allow to access the input? So think of a black box that contains this input x. Okay. And the only way that algorithm can access x is by querying, or it's by probing some I, which takes value from 1 to n into this black box. And this black box returns the bit xi. Okay. And and then the algorithm wants to compute fx for all x by making minimum number of queries. So the number of queries is the only cost that the algorithm has to pay in this model. And the correctness requirement that we are going to stick with is that we want the algorithm to compute fx for all x correctly with probability at least 2/3. So here is a toy example, right, of a function. So there's a function on 2 bits. The name of the function is balanced or constant. So can you see my mouse and the stuff that I'm trying to highlight?
Yes.
Okay, great. So here is this toy example called balanced or constant. There's a function on 2 bits which takes x1, x2 as input and outputs 1 if the string x1, x2 is balanced, right? If it's 0, 1 or 1, 0, that is the number of ones is same as the number of zeros. And it outputs 0 if x1, x2 is a constant, if it's all zeros or all one string, right? And it's easy to see that the classical query complexity for this problem is 2. Okay, so 2 classical queries are necessary and sufficient. So it's quite easy to like if we query both bits, right? If we, let's say this black box contains x1, x2, and we first ask for x1 and then ask for s2, right? So by making 2 queries, we know the entire string x1, x2. Okay. So we can in particular compute this function balanced on constant. Okay, we know what the string is. And one can also easily prove a lower bound. And I'm not going to discuss the proof of the lower bound. But now let us move on to the quantum query model. Is the classical model clear?
I have a doubt.
Yeah.
Is it always possible to construct such a classical query model efficiently, in the sense that you said that the function takes in as input as 0, 1, n bits as input and gives 0 or 1 as output? Is it always possible to construct such a black box efficiently, in the sense that the number of queries should not dominate the entire algorithm, right?
Yeah, that's a very good question. So that's why like this model is a bit weaker than some other models of computation. Okay, for example, if you have a Turing machine in mind, right? Then the cost of coming up and running the algorithm is a part of the model, right? But what this model tries to do is that it tries to extract away the complexity of the algorithm. Okay, and it only tries to capture how many times you have to look at the input in order to compute the function.
So one more question. So is it always possible to create a query for such a function? I mean, for any
Yeah.
possible function, is it always possible to create an efficient query, efficient black box query? I mean, efficient black box.
Yeah, I think it is possible in the classical set. So for example, I mean, by efficient, one has to give up some space in order to do that. So in general, I don't think it will be possible for all functions, right? But this becomes useful when this function f, has a succinct description. So let's say there is some model of computation. If you can compute this function efficiently, then you can come up with such a black box efficiently.
Okay,
So
thank
in
you, sir.
general, yeah, it's not possible to construct a black box efficiently for all functions. But for several interesting functions, it should be doable. So as it turns out, one of the reasons why this model is useful is that once you come up with an algorithm in this model, in the query model, you can often get an efficient algorithm in the usual model, right? So for many functions, it is indeed possible to
So
construct
here,
this black box. Yeah.
our assumption is that the query model, the
Mhm.
complexity of query model should not dominate the entire algorithm, right?
Yeah. So the assumption is that the cost of the rest of the algorithm does not matter. Okay. In this algorithm, only thing that matters is the number of queries that we are making. Okay.
Provided
So
the
what?
queries, the number of queries does not dominate the complexity of the algorithm, right?
Well, we are not going to count anything except the number of queries for the cost of the algorithm.
Okay, thank you. Yeah.
Yeah. Good. Any more questions? Okay, great. So now let us move to the quantum query model, right? And here everything is identical to the classical model, except now we are trying to come up with a quantum algorithm. Okay? So before we try to come up with a randomized algorithm, now we want to come up with a quantum algorithm. And now, so let me now try to explain what a quantum query model is going to do. So like there are 4 parts to a quantum query model. So first is states. Okay. So states are unit vectors in a suitable vector space. Okay, so these are going to be vectors in a vector space, and these have going to have length 1 in the L2 norm, right? And states, think of states as the memory for the computation. So all the manipulations that we are going to do are going to be done on states. All right. But how are we going to do these manipulations? For which we are going to use unitary matrices. Okay. So all algorithms in quantum computing are unitary matrices. All right. And since we are working with a query model, we are going to have a special unitary matrix, which we are going to call the query oracle. Right. We'll see an example of this soon. And finally, so till now, what was happening is that everything was happening in this quantum world. There was some state, it was manipulated by matrices. But at the end of this process, we need to get classical result, right? And for this, there is this rule called measurement. So it's a very simple rule that defines how to obtain classical results from a quantum computation. We won't be defining measurement in this talk, but because it is not relevant today, but we'll see an example of this, and we're going to do this next. All right. So again, so consider again our favorite function, balanced or constant. All right. And now here we are going to assume that we have access to this oracle, which is usually called as phase oracle. So this oracle is a matrix whose 2 by 2 matrix, whose off diagonal entries are 0, right? And whose diagonal entries are -1 to the x1 and -1 to the x2, right? Since we do not know x1, x2, we do not know what this matrix is. Okay. And now here is the algorithm. So first we start with the state ket 0. Okay. So this symbol, a vertical line followed by 0 followed by angle bracket, this is known as ket. Okay. So we start with the state ket 0, which is defined to be the vector 1, 0. All right. Then we apply this matrix H2. Okay. This is a unitary matrix. Then we perform a query. Okay. That is, we apply this matrix. Then we again apply this matrix H2 and then we measure. Okay. So let's see what this algorithm is doing. So we are going to trace the state of the algorithm after each step. Okay. So after, well, in the first step, the state was this vector 1, 0. So what happens after the second step? We apply this matrix H2, right, on the state 1, 0. So we get this vector 1 by square root 2, 1, 1. In the step 3, we make a single query, right? And after this, what this means by making a query, it simply means that we multiply the matrix, the query matrix, the query oracle, by the state that was present, the state just before that. And the state was 1 by square root 2, 1, 1, and we get the following state. All right. And then we again in step 4 apply once more we apply H2, right? And turns out that if you do the calculation, you'll find out that upon applying H2, if the string is balanced, right, we'll get a vector which is of the form 0 plus minus 1. And if the string is constant, we'll get a vector which is of the form plus minus 1, 0. Right. So the important thing to note here is that these two vectors are orthogonal, okay, irrespective of the sign. And turns out that there is a measurement that can distinguish between all orthogonal vectors with probability 1. Okay. So does this make sense to all of us?
We just wanted to check in step 4, after multiplication, you are using some expansion there.
Yeah. So I mean, -1 to the x1 is same as 1 minus 2 x1 for x1 being 0, 1, right? So I'm just using that and writing that here. Yeah. Okay. So the important step in this algorithm is this step 3, where we were applying the single query, right? So notice that by making this query, we are in some sense able to access information about both x1 and x2, right? So this is called making queries in superposition. All right. And what we have seen in this algorithm, so recall that a couple of slides back, we looked at the classical algorithm for this problem. Okay. And we argued that 2 queries were necessary. But the quantum algorithm can solve this problem by making only one query, right? So this problem is known as Deutsch problem, and it can be generalized a bit more to the so-called Deutsch-Jozsa problem, and which was the first problem that gave exponential separation between deterministic and quantum query complexity. Okay. So let me mention one more problem. This is the problem, this is a function that all of us are familiar with, the OR function on n bits, which evaluates to 0 if and only if the input is the all 0 string. All right. And a slight modification of this problem is the unstructured search problem. And again, it's not too hard to show that the classical query complexity of this problem is omega n. Okay. And the Grover's algorithm solves this problem with order of square root n queries. Okay, so this is a fact. Great. So now let's go to the noise model. All right, and we'll start by giving a classical analog of the noise model. Okay, so consider an algorithm A that solves some problem. Okay, let's say it computes fx on input x by making at most q queries. So given input x1 through xn, the algorithm is going to make q of queries and going to evaluate fx for all x. But now instead of getting this true input x1 through xn, the algorithm gets input y1 through yn such that each yi is equal to xi with probability 2/3. Right. So this is the promise. So what is happening? The algorithm does not get a true input, but it gets a noisy version of the input. Okay. Each yi is going to be equal to xi with probability 2/3. So here is a question that I want to ask. So can we make this algorithm A robust to noise without blowing up the cost too much? Any ideas? Can we do this?
You could add some structure to the outputs xis in the form of a code, a classical code.
Yeah.
Create create three copies and do a majority voting based on each bit. So we'll get the higher the value of bit is the correct one.
Exactly, that is the idea. But we would like to do a bit more than three copies, right? Because the algorithm makes Q queries, right? So yeah, so as you mentioned, we'll take log Q. So for every query that this algorithm A does, right? Our modified algorithm will make log Q many queries and take majority. Okay. And then one can argue that the error probability has become much smaller than it has become something like, let's say, 1 by 100 Q. And then a union bound would imply that the error probability of the modified algorithm does not blow too much, right? So does it make sense? Repeating, querying a bit multiple times and taking majority. Okay. And the quantum noise model that we are going to work with is analogous to the classical model, right? And here again, the oracle behaves correctly with probability 2/3, and with probability 1/3 it acts as identity. And this noise model is known as the faulty oracle model. It's a definition of the noise model that we are going to work with. So an important point to note here is that the quantum noise is fundamentally different from classical noise, right? So in the last slide, we saw that we could reduce the classical error by just order log Q blow up. So this is not something that we can do in the quantum world. And why is that? So the unstructured search problem, or the OR function of n bits, has classical query complexity omega n, while quantum query complexity or the square root n, right? If we could do error reduction in the quantum case, just as we did in the classical case, we would have a order of square root n log n quantum algorithm, even under the faulty oracle model. But a result by Regev and Schiff from 2008 showed that under the faulty oracle model, the quantum query complexity is omega n. Okay. So under some error, the advantage is completely lost. So let me now mention a little bit of prior work that has been done for various noise models.
Manaaswi, I have a basic question.
Yes.
On the quantum query model. The example that you gave, if you can go back a couple of slides.
Sure.
Yeah, so there, the oracle is just a unitary matrix, right? So,
yes.
So if you query the oracle, it returns this matrix -1 power x1 and -1 power x2, right? So,
Yes. Yeah, so when we query the oracle, we apply this matrix on some vector. So
on the vector, okay. So my question is like, whenever we query the oracle, it always oh, it doesn't return. Okay, I get it. So you query the oracle with the vector, and it returns. It applies the matrix and returns.
Yeah. Okay. So we start with some state, and whenever we apply an oracle or any algorithm, we just multiply this vector with some matrix.
Okay. Okay.
Yeah.
So I see. So this vector is sort of serving the role of I in the classical model, where you are querying the oracle with an I and it returns xi.
Exactly,
Here
exactly.
you query
Yeah.
with a vector and it returns the
Yeah,
matrix applied to the vector. Okay.
Yeah. So for example, if we chose to query with the vector 0, right? If we chose to query the oracle with the vector 0, then we'll end up with the first column of the oracle, which contains the value of x1. Right? It's exactly a classical query. Yeah.
Get it. Okay. Okay. Thanks.
Thanks. All right. So the faulty oracle that we looked at is an example of irreversible noise in quantum computing. Okay. By irreversible noise, I mean that the action of this oracle cannot be described by a unitary matrix on all vectors. Okay, this can be done by a concept known as CPTP maps, but we'll not be talking about this today. And turns out there is another kind of noise that people have studied a lot, which is known as reversible noise. Okay, and and it is known that if the noise is reversible and we have access to the both the unitary that corresponds to the noise and its inverse, then we can make any quantum algorithm robust with at most a logarithmic overhead. And the idea is that the majority trick that we looked at a few slides back works even in the quantum case. And the situation with irreversible noise is more interesting. And as I mentioned before, a lot of work here has been on the unstructured search problem, and in particular, the Grover's algorithm, right? And among these papers, the paper RS08 has been quite important. So first, because it gave a lower bound for the unstructured search problem in the noise model of the faulty oracle. So naturally, it influenced the papers that followed. And recently, this paper has been used quite a bit in the discussion of this data structure known as quantum RAM or QRAM. Okay, so QRAM is a highly debated topic today in quantum computing. The debate is whether it's realistic or not, right? And this lower bound by RS08, Regev and Schiff from 2008, has been used by a few papers to argue that the RAM model is not realistic. Okay. And finally, let me mention this paper also from 2023 by Childs et al. And they study another famous problem known as Simon's problem under a noise model known as depolarizing noise model. Okay, this noise model is arguably more natural than the faulty oracle model that we consider in this paper. Okay, we'll talk about this more in the open problem section. Okay, with that, let me come to the statement of our main result. So our main theorem is the following. So let's say there is a quantum algorithm A that computes fx for all x in domain of some function f by making at most q queries to a fault-free oracle. All right. Then there is a quantum algorithm A prime that computes f by making at most q cube log q queries, okay, to a faulty oracle. Okay. And recall, this is the definition of the oracle. And we show that this can be done for all p at most 1/2. All right. So in other words, what this theorem says that if there is an algorithm that makes q query on a fault-free oracle, then by a near quadratic blowup, we can make it tolerant to the noise of a faulty oracle. And a few remarks for this theorem. So first, this theorem holds more generally for relations. Okay, I've stated it here for functions on partial functions, but it holds more generally for relations. And this is important because there are many relations for which quantum algorithms are known to have a exponential speedup. Okay. So clearly the theorem implies that if there is cubic speedup for some problem, then there is some quantum advantage retained even under the faulty model. And in particular, if there is super polynomial or exponential quantum advantage, then this advantage is retained even under the faulty oracle. So any questions on the statement of the theorem?
Couple of questions here. So firstly,
yes,
can this be interpreted as an upper bound for this?
Yeah, this is an upper bound. Yeah.
Secondly, then in this statement, like Grover search algorithm, like all those things won't give advantage, right?
Exactly.
According to
Yeah.
this.
Yeah. So Grover's won't give advantage, and so we also know by a previous result that Grover's is not going
That
to give
R is
advantage.
0, right?
Yeah, exactly. Yeah.
Okay. And this faulty oracle is considered for in R is 0, it was it P 1 by 3 and 2 by 3, or it was also for any P?
Yeah,
Less
so
than.
so P 1 by 3 or 2 by 3 is, P constant is the the important thing. Yeah, so they considered for P equal to half. So the lower bound that they gave was for P equal to half.
P equals to half, not
Yeah,
less
yeah.
than half.
Yeah,
Okay.
but the lower bound holds for any constant smaller than half.
Okay, and because in Grover search they give like the probability is always greater than half, so it won't lie in that space.
Yeah, so this P is the error, the probability with which the oracle fails to act, right?
Yeah, so it will be less
So
than half always.
yeah, so that's going to be, so it's natural to consider that it's less than half. So that is a natural choice. I mean, it can be closer to 1 also, but and we believe that our algorithm should work even when this probability is close to 1, but we don't have a proof as of now.
Okay. Thank you.
Any more questions?
One quick question.
Yes.
So are there examples of natural problems where we get supercubic quantum query advantage?
Yeah, for example, for factoring, there is a exponential speed up in the query model. So
Okay.
yeah. So for all algorithms that are of the form like period finding kind of algorithms, for most of those problems there are exponential. So,
I see.
yes.
Yeah, one more quick question on this. So,
Yes.
like, can you comment on where this the new algorithms like QAOA stand in this picture? Like, they are not in this model, but do they also
QAO is
compare?
also studied in this model.
Okay.
Yeah.
So where do that stand in terms of this complexity?
So I think QAO is like more like Grover search, and they stand like small polynomial speed up, I guess. Yeah, I'm not 100% sure, but I'll have to get back to you on this. But I think QAO usually gives a small, so it's a quantum walk based algorithm, if I'm not wrong.
No. QAOA is basically they do a hybrid algorithm where there is a quantum, so they use a quantum computer to evaluate the cost function, and then they minimize the cost function in the classical domain using a classical optimizer. And then that loop is repeated for until convergence. Yeah.
Yeah, so I'm not sure about, I have seen some papers in the query model, but I'm not sure where that falls.
Okay. So,
Yeah.
thank you.
Thanks. Okay, so let me now proceed with the proof ideas. So how much time do I have? It's around 20 minutes, something.
Yeah, you have around 25 minutes, yes.
Okay. Great. All right. So let us start with a Q query quantum algorithm. Okay. And let's call this algorithm A. And how is this algorithm going to look? It's going to start with some initial state. All right. Then this algorithm is going to apply, some unitary, will manipulate the state somehow. Then it will make the first query. And after making the first query, it will again manipulate the state, make the second query, and so on. Okay. So in this way, algorithm makes Q queries, right? But now we are in the situation where these oracle calls are faulty, right? So these are no longer true oracles. So the way in which we are going to obtain the robust version of algorithm is the following. So we'll replace with each oracle call with a subroutine E, such that E is going to make at most Q square log Q queries to the faulty oracle. And furthermore, it will have the guarantee that the output of E and OX is very close to each other for all possible inputs, right? So the output of E and OX are going to be vectors, right? Because we are always working with states. And when I say they are 1 by 100 Q close, I mean in the L infinity distance. Okay. So our goal will be to come up with such a construction. And if we are able to do this, then, well, first of all, we'll blow up the query complexity by this multiplicative factor, right? Q square log Q. And the second thing that will happen is that error probability will increase additively by at most 1 by 100, right? So this is the big picture proof idea. And now we'll go into the details. Any questions here?
One quick question. When you say E is a subroutine, will it also apply only unitary transformations?
Exactly. Yeah. It will only apply unitary transformations. Yes.
Okay.
Yeah. So yeah, in fact, So yeah, okay. We'll soon see the subroutine E. So yeah, it will become clear. Yeah.
Can you add on this 1 by 100 Q close thing a bit?
Yeah, well, so this is like, I mean, the states are going to be, so if the states are very close to each other, so let's say this property is satisfied in the final state also, right? Okay. Then those two vectors are so close to each other that on any measurement, their output is not going to differ by a lot. Okay. This can be made formal, but yeah, requires to define a few more things. But I hope it makes sense intuitively.
Okay.
Yeah. All right, and so let me be a little bit faster. Okay, so we looked at the phase oracle before, right? But now we are going to work in the more general setting of standard oracle. Right, so this is the most general setup in which we study query complexity, and for which let me define a couple of things. So first, we are going to define these vectors ket I for I in 1 to n, and ket I is simply the standard basis of Cn. Okay, C to n. So for example, ket 1 is the vector 1 followed by all zeros, ket 2 is the vector 0 1 followed by all zeros, and so on. All right, and we have already been looking at these vectors ket 0. Okay, and ket 1. So ket 0 is the column vector 1 0 and ket 1 is the column vector 0 1. All right, and here is the definition of the standard oracle. So let's look at this picture first. So the standard oracle is going to be a matrix that is going to take the vector ket I and the vector ket B as input. Okay, ket B is going to be 0 or 1, and it is going to return the vector ket I and ket of B XOR with Xi. So in particular, if B is set to 0, then the output of the target oracle is going to be Xi, right? Okay. And this qubit gets a special name called target qubit, and this is a name that we'll be using throughout and the rest of the talk, right? So this picture is written more formally in terms of tensor product, and this is the notation that I'm going to avoid for the rest of the talk, but this is the standard notation. Okay. All right. So we already defined the phase oracle. So I should mention one more thing, that usually when we think of queries, as it was discussed a few times before, as Chandan also mentioned, that the query to, because there's a matrix, and by querying, all we are doing is evaluating vectors on this matrix. So a general query to this matrix is of the following form, like a general vector in a suitable space, general unit vector in a suitable space. And when we make our algorithms robust, we have to make sure that the algorithms work against all such unit vectors. Okay. Right, so this is the definition of the standard oracle. And let us recall, before moving further, the definition of the faulty oracle. The faulty oracle OX half is going to act as OX with probability half and as identity with probability half. All right. And in the rest of the talk, we are going to focus on how to correct error when the input is of the form ket I, ket 0. So this is the only thing that we'll focus on in detail. And at a very high level, I'll mention what we do for the general states when the input is the general state. Okay. So here is the circuit that corrects for error when the input gets 0. Right? So looks a bit complicated, but it's going to be very simple, as we'll soon see. Right? So let me say first a few things about the circuit. So the input up to the circuit is ket I, ket 0, right? So these are the only states that we are going to focus on in this talk. We want to correct errors on these states. And what do I mean by this? By this, I mean that we are going to use this noisy oracle in such a way that the output after the circuit is applied should be ket I and something that is very close to xi. Okay, so this is our goal, right? And so what does the circuit do? So it applies a rotation some rotation in the beginning, which I'll soon explain, applies another unitary, and the circuit does t times for a parameter t, which is chosen to be ordered q square log q, and also even, which again we'll see soon. And then it applies the same unitary once more. Okay. And the entire analysis of the circuit is going to be done in a two-dimensional subspace of C2, okay, which is going to be the span of ket 0 and ket 1. And this is the state where the target qubit lives. Okay. So the input qubit, the qubit I is like fixed, right? So we only are interested in analyzing what happens to the target qubit. All right. So yeah, if it is confusing, I hope it will soon make sense. All right. So in fact, let's see what happens when we apply the first gate. Okay. So initially, the target qubit was here, along the x-axis, along ket 0. So when we apply the first gate, it rotates this vector ket 0 in a counterclockwise direction by an angle of pi by 4. Okay. Is this okay with everyone?
Is this different from the H matrix that you mentioned in the previous case?
Sorry, which matrix?
Is this different from the H operator you used for the first example?
I don't recall using an X operator.
Sorry, H operator.
The H operator. I think it is. Yeah, I think it is. Is it different? Yeah, just this action is not different. I mean, even if you apply H, right? That's completely correct. Okay. So the action of H operator on 0 and R minus pi by 4 on 0 is same, right? But I'm not sure if H operator but it's not same on all vectors.
Oh, right.
So this is a matrix, like we can just write down the I think they are the same matrix, right? Yes. So R minus theta is, it's like a 2 by 2 matrix where the entries are cos theta minus sin theta and so on. Okay. Yeah. But let's not go there. So what R minus pi by 4 means is rotation in counterclockwise direction by angle minus pi by 4. Okay. All right. So now let us consider. So this was the easy first step. Now let us consider another easy case. Now let us consider the case when xi equal to 0. All right. Then I claim that this oracle has no error at all. Okay. And why is that? Because, well, with probability half, the oracle is going to act as identity. Okay. And with probability half, it acts as OX, right? But when xi is equal to 0, then OX itself acts as identity. Okay. Fine. So if xi equal to 0, then basically we can replace this part of the circuit by identity, right? Then what does this entire part do? This rotates by angle r by 2 pi in clockwise direction t times, right? R by 2 pi t in t times, which is same as rotating by angle pi by 2, right? So in that case, we get the following vector, right? So this vector now gets rotated by angle pi by 2 and it goes here. And the last step of the circuit rotates it again in counterclockwise direction by angle pi by 4. And the final state is here, right? So what have we concluded till now? If the input I is such that xi equal to 0, then on input I0, we get the value I0, as expected, right? Does it make sense? So at least the circuit performs correctly when the input was, when I satisfies xi equal to 0. Is this okay? Right. So now let us move to the harder part. Okay. The case when xi is equal to 1. Right. And let us start with a sanity check. Okay. So the way we are going to do sanity check is that we are going to take this noisy oracle and replace it with the true oracle. That is, we'll assume that p is equal to 0. And this circle better work in that case, right? So let's see whether it works or not. So here's a very crucial observation for the, we will be using it throughout the rest of the proof. The observation is that if xi equal to 1, then the action of this oracle OX, in the two-dimensional space in which the target qubit lives, is reflection about this line y equal to x, right? So let us look at the two-dimensional subspace of the target qubit. This is ket 0, this is ket 1, and this is the line unit vector along the line y equal to x, right? What happens when we apply OX for some I such that xi equal to 1? Well, we get the same vector, right? Okay, so this vector is fixed. And if we take any vector that is orthogonal to vector to this line y equal to x, so this is, for example, this is unit vector along such a vector, then we get a -1 sign here, right? So this proves that OX acts as a reflection in the state as a reflection when xi equal to 1 in the space of the target qubit. Okay, is everyone fine with this? Right. Great. So now let's see.
Maybe,
Yeah.
Sorry to interrupt. We are missing something obvious. Where are you using the fact that t is even?
Yeah. Now I'll use that fact now. Yeah.
Okay.
Yeah. So now we are in the case when xi is equal to 1, and now we are seeing what happens to this, what this circuit does, right? So before this circuit was applied, we were in this state, right? So on the first application of OX, well, OX acts as, is a reflection about the line y equal to x, so it does nothing to the state, right? Then we do a rotation by pi by 2. So this angle rotates clockwise by an angle of pi by 2, right? OX now reflects this state by an angle, reflects this state about y equal to x. And then when we do one more rotation, we come back to the state to y equal to x, to the line y equal to x, right? Is this picture clear? I mean, if you just stare at it, I hope it will become obvious. Okay. So the key point, as Chandan mentioned, is that in two rotations, we come back to the state where we started, right? And since we have chosen this to be even, after all of this rotation, we'll be in this state, state y equal to x. And then if we rotate this thing, like the final step of the circuit, by minus pi by 4, we go to the state 1, okay, which is the desired output. On input I0, when xi equal to 1, we wanted to get the output ket 1. Is this slide clear to everyone? Because this is like the last technical slide, and then we'll try to wrap things up. Okay. So now let us consider the noisy case, right? In this case, we have this oracle OX half, and with probability half, it is going to act as reflection about y equal to x, and with probability half, it acts as identity. So, like if we see what this oracle does in two cases, in one case, when the state is to the left of the line y equal to x, and in the other case, the state is to the right of the line y equal to x. We see that, in one of the cases, the angle decreases, and in other cases, the angle increases for each of them, right? And since the probability p is half, all of these, an increase of angle pi by 2 or decrease of angle pi by 2t is going to happen with equal probability, right? And turns out that, this can be captured by a standard random walk in a two-dimensional space, and it can be upper bounded by the so-called Leve's inequality, which is a concentration bound. And if we choose, so yeah, so Levy's inequality intuitively allows us to apply something that is close to Chernoff bound, to bound the deviation of this vector from y equal to x. And if t is chosen to be order q squared log q, then the resulting state can be shown to be 1 by q close to the line y equal to x. All right. So this was, I went very quickly over the slide. So I think I'm running out of time. Yeah, but I hope the idea was clear. Any questions? Right. Great. So till now we only saw how to deal with the error when the input state is catic at 0. But a general state can be much more complicated than this. And to make the proof work for a general state, we have to add an extra register or an extra space called this, which we are going to call S. All right. So this was the circuit that we discussed, F, right? Let's call this circuit F. The final circuit is going to be the circuit E. And this register that I talked about here is here, this register S. And we argue that during entire computation, entire a single error correction procedure, all the error is going to accumulate in this register S, right? And furthermore, when we add the error over Q queries, the total error is going to be small. Okay. So I'm just mentioning this at a high level, not going into details. So since I'm almost out of time, let me finish with a few open problems. So I think there are many problems that are quite interesting to me in this line of work. So first of all, we showed that a quantum advantage will be retained under a certain noise model with a quadratic overhead, but we don't know whether this procedure of error reduction is tight for all functions, right? Furthermore, it is possible to have better error reduction for specific problems, right? For example, if someone focuses on the factoring problem, then it's possible to do it with a linear overhead instead of a quadratic overhead. So that might be interesting. And perhaps the most interesting of these questions is that can we make query algorithms robust to other noise models? So there are two, other than this faulty oracle model, there are two important noise models to consider, which are very closely related to each other. These are called depolarizing and dephasing noise. And yeah, so I find it to be very interesting to see whether query algorithms can be made robust to this type of noise. Yeah, and that's all from my side. Yeah. Thanks a lot. Any questions? I'll be happy to talk about.
So one question I had, like,
Yes.
how realistic is this faulty oracle model? Like, how does it relate to the current quantum computers that, say, IBM have?
Yeah, I don't think it is that realistic. Yeah, so these noise models are much more realistic. For example, depolarizing and dephasing noise. So yes.
Yeah, thank you.
Yes. So, well, I mean, it is useful in the following sense that, like it's a weaker noise model. I haven't defined depolarizing and dephasing noise, but like if maybe you can check later on, or we can talk about it, that the faulty oracle is a weaker noise model. So, if a lower bound holds against a weaker noise model, it's expected to hold against a stronger noise model, right? So before what we showed, so there was only one lower bound known for the unstructured search problem, right? And a few people believed that a lower bound would hold even for all problems. So now with this result, when we know that, okay, at least under the faulty oracle model, a lower bound is not going to hold for most problems, then it becomes more natural to try these other noise models, depolarizing and dephasing noise, to find out what is happening for these noise models. Does it make sense?
Yeah. Thank you. Is there a research where this relation between these noise models are established? Because that faulty noise model seems a bit strong, as it said that, okay, in the failure case, it's identity. But in general, there will be some success probability, right? So that's where
Yeah, even in the faulty model, there is some success probability, like right, with some probability it's going to be act as it should probability have. Yeah, and regarding reference, so there is no clear-cut relationship known between these models. But a great place to check is a recent paper by Ansis Rosmanis, and it's the name of the paper is, I guess, yeah, it's a paper from 2023. It's like query complexity of search under noise, or something like that. Yeah.
Okay. Thank you.
Thanks, Manaaswi, for the nice talk. I have a couple of questions.
Yes.
Very basic questions. One is, I mean, I don't know much about quantum computation, that's why I asked this basic question.
Please.
So, can you say a few things about the measurement? I'm trying to understand that process.
Yeah.
So, because that is what connects the quantum world to the classical
Exactly.
world.
Yeah.
Right.
Yeah.
So that says, can I assume something like that? Our goal while designing the quantum algorithms is to finally sort of create vectors which are sort of far apart, meaning almost orthogonal to each other, so that in the measurement process we can distinguish them. And,
exactly. Yeah. Yes.
So, right. So, yeah. So, I mean, is this the right view to have?
Yes, exactly. Yeah. So this is the right view. In fact, in the setup of query complexity, where it's possible to prove lower bounds, yeah, most of the lower bounds are proved using what you just suggested, by showing that after a certain like so many operations, not all vectors are going to be far apart from each other.
Okay. Yeah, thanks. The other question is also basically related to the other noise models that you mentioned.
Sure.
Is there any crude upper bound known at least? I mean, not polynomial upper bound from Q to QQ, but for the other noise models, like, is there any kind of a, slightly non-trivial upper bound known?
Yeah, I mean, so I don't know of a non-trivial upper bound, but we can say like a few things we can always say. For example, there are some. So if we look at query algorithms, we can think about query depth, like how many queries have to be made in succession, right? And for algorithms that have low query depth, again, one can argue that under all noise models, let's say the query depth is constant, then we can argue that under all noise models, quantum advantage is not lost. But beyond that, I do not know of any non-trivial upper bound other than what I presented today.
Okay.
Yeah, we believe that this should work for more generally for other noise models, but we haven't been able to prove it as of now.
Thanks.
Yeah, thanks for the question.
So if there are no further questions, then let's conclude that talk. Manaaswi, thank you for a very informative talk.
Thanks a lot.
Yeah, thank you. Thank you for the nice talk.
Thank you.
Bye.
Bye.